Welcome to Fundamentals of Hypothesis Testing Methodology. This is the first lesson of 3 for this unit. In this lesson, I'll provide an introduction to hypothesis testing, discuss how to choose a test, and then interpret its results, and provide a short summary of the lesson. Let's start with hypothesis testing, and what is it? Hopefully, the information on this slide about research questions and hypotheses is familiar to you already, but it never hurts to review. With research questions, we are formulating what we want to know. These should be able to be written as questions. For example, what is the average height of students at the African Institute for Professional Development? With our hypotheses, we are making a prediction about something. This prediction is often the relationship between some variables of interest, or the effect of some variable or action on another variable. Hypotheses should be able to be written as declarative statements. For example, the average height of students at the AIPD is 1.7 meters. The type of hypotheses we want to test and the type of data we have determine the type of test we will use. If you were to search for steps in conducting a hypothesis test, you would find lists of steps ranging from 3 to 7 steps. Some of the steps wouldn't even follow the same order as this list here. But this is the basic process that we'll follow in this lesson. The reason for the differing number of steps is that you can formulate your research question, and thus your hypotheses, to ask a number of questions about your data, including about the shape of your distribution. For instance, you could ask if the daily number of homicides in the United Kingdom follows a Poisson distribution. You can use a goodness of fit test, such as the chi-squared goodness of fit test, in order to test that hypothesis. Moreover, the number of individual steps really depends on how specific an author is in describing the steps. Before we can get started with hypothesis testing, we first have to understand the nature of the statistical problem that we want to solve. When we have only one sample, we can't compare the statistics of multiple samples. Rather, we typically ask if the statistic from the sample that we do have is higher or lower than some other value. For example, is the average height of students from the AIPD higher or lower than 1.7 meters? We call this a one-sample hypothesis, or one-sample problem. When we have 2 or more samples, we can compare statistics from the different samples. We call this a two-sample hypothesis, or problem. In the case of 2 independent samples, the members of the 2 samples are different people, such as a test and a control group. For example, are the students of AIPD taller or shorter than the general population of Rwanda on average? In the case of 2 dependent samples, the members of the 2 samples are the same people. The samples may have been taken pre- and post-experiment, or they may have been taken longitudinally. For example, are students of the 2020 AIPD graduating class taller or shorter than those of the 2021 graduating class? When conducting hypothesis testing, you will always have at least 2 hypotheses, the null hypothesis and the alternative hypothesis. The observed values, the data that we are working with, will always include some variation due to chance. However, we can ask if the variation in the observed values is due to chance alone, or if there is a real relationship or effect that is also observed. The way we formulate this is the observed statistic of our sample is equal to some value. For example, the average height of AIPD students is 1.7 meters. The alternative hypothesis is formulated as the observed statistic of our sample data is not equal to some value. In this example, we could say the average height of AIPD students is not 1.7 meters. This is also the stage at which you'll identify the relevant statistic. What values are you trying to compare? The number of coin flips? Mean heights or weights? What is the most relevant statistic for your research question? It is important to remember that when we test our hypotheses, we are not proving that our alternative hypothesis is true. Instead, we are saying we believe we can reject the null hypothesis in favor of our alternative hypothesis. Therefore, we are not conducting equivalence tests in which we prove that a parameter is equal to a predefined value, or that two parameters are equal. While we won't be covering equivalence tests in this course, you can investigate them more on your own. So next, decide if you're interested in a one- or two-sided alternative hypothesis. Both one and two sample problems can be tested with one- or two-sided hypotheses, although it is more common to test one sample problem with a one-sided hypothesis. With a one-sided hypothesis, we test to see if one sample statistic is less than some value, or the same statistic from another sample. We can also test if the statistic is greater than the value or other sample statistic. For example, a null hypothesis could be that AIPD students have an average height less than or equal to 1.7 meters, or that AIPD students have the same average height of the general population of Rwanda. The alternative hypothesis in the first case would be that AIPD students are taller than 1.7 meters on average. An alternative hypothesis in the second case could be that AIPD students have an average height less than the general population of Rwanda. With a two-sided hypothesis, we test if one sample is not equal to the other. Our null hypothesis is that the two samples are from the same population, so the observed statistic will be the same. Our alternative hypothesis is that the two samples are from different populations, so they will have different observed statistics. Now let's consider how to choose the appropriate test for your hypotheses. How do you choose a test? A choice of a hypothesis test is dependent on three characteristics of, or assumptions about your data. The first is that your data is independent. The chi-squared and other independence tests are a good way to test the independence of your observations. If your hypothesis is focused solely on whether your observations are independent, then you can stop here. If your data is not independent, then you can use a paired t-test for dependent data. The second assumption is that your data follows a normal distribution. If you need to test the shape of your distribution, i.e., whether or not you have a normal distribution and your data is parametric, then you can use the chi-squared and other goodness of fit tests. If you have non-parametric data, then you'll need to consider the Wilcoxon-Mann-Whitney test. The third assumption is that your variance is homogeneous or equal. If it is, you can use a Gauss test if the variance is known, or a t-test if it is unknown. If you don't know if your variance is equal, then you can use a Welsh test. As you can see, there are quite a few possible tests that you may want or need to use for testing your hypotheses. We will not cover most of them in detail, but in the next 2 lectures, I'll discuss Z and t-tests and ANOVA. I recommend that you read about each of them. I've noted some important characteristics of each test. Choosing the appropriate test will depend on the characteristics of your data. Now that we've looked at how to choose a test, let's discuss how to interpret the results and draw conclusions. Although we're not quite ready to make a decision about the results of our hypothesis test, we need to think ahead to ensure that we don't draw the wrong conclusion. One way to think about how to evaluate our findings is using a confusion matrix, like the one on this slide. A confusion matrix helps visualize possible conclusions. Here, there are 2 types of correct conclusions: true negatives and true positives, and 2 types of incorrect conclusions: false negatives and false positives. We call the incorrect conclusions type 1 and type 2 errors. For example, let's have as our null hypothesis the claim that none of these images are of hot dogs. For the images in the first row, we see that our null hypothesis is true, meaning neither picture is of a hot dog. Looking at the first image of the pizza, if we accept the null hypothesis because it is true and conclude that a pizza is not a hot dog, we would be correct. However, if we look at the picture of the dog in the hot dog costume and reject the null, thereby concluding that the dog is a hot dog, we would be incorrect. This false positive is a type 1 error. The probability of making a type 1 error is equal to the probability of accepting the alternative hypothesis instead of the correct null hypothesis, and is given by alpha. With the images in the second row, we see that our null hypothesis is false, meaning that both pictures are of hot dogs. So if we look at the picture of the chili dog and accept the null, thereby concluding that the chili dog is not actually a hot dog, we would be incorrect. This false negative is a type 2 error. However, if we see the picture of the classic hot dog and reject the false null hypothesis, we would correctly conclude that we have a hot dog. The probability of making a type 2 error is equal to the probability of accepting the false null hypothesis instead of the alternative hypothesis, and is given by beta. Now that we know about the types of errors we can make, how do we make sure that we don't make any errors when we make our decision about the null hypothesis? We conduct a significance test. A significance test allows us to determine how likely it is that the test statistic is not due to random variation. If it is very likely that our test statistic differs from the null hypothesis for non-random reasons, meaning the sample is truly different, then we can reject the null hypothesis We call this likelihood, or probability, the p-value. Let's consider the XKCD cartoon here. Aaron says that he is dating a number of people, and that while he might see one person more than the other, it is due to random chance. So Marcia may be studying for exams this week, so he spends more time with Felicia and Tanya. But over time, he claims that he spends the same amount of time with all the women. That is his null hypothesis, that there is no true difference in the amount of time he spends with any single woman. However, Tanya says she's an outlier. Her alternative hypothesis is that Aaron spends much more time with her than he does with Marcia or Felicia. If she can calculate a p-value that falls below a pre-specified alpha level, Aaron should reject his null hypothesis and call himself Tanya's boyfriend. How does this relate back to our type 1 and type 2 errors? Our significance level, alpha, is essentially an indicator of how willing we are to make a type 1 error. Remember that type 1 errors mean we reject the null hypothesis even when it's true. For Aaron, this could mean breaking up with Felicia and Marcia, even though he doesn't actually spend more time with Tanya. But it could also mean incorrectly rejecting a null hypothesis of innocence in a criminal trial and convicting an innocent person. Since type 1 errors tend to be the more severe errors, we try to minimize our alpha and maximize our confidence that we will calculate a statistic that will not allow us to falsely reject the null hypothesis. Common values for alpha are 0.05 and 0.01. Since we're looking at values distributed around the mean, we subtract alpha from 1 to calculate our confidence level. The power of the test is the probability of not making a type 2 error and thus correctly rejecting the null. In order to minimize beta, we need to account for it in our sample size calculations, which was covered in Lecture 6. So now let's pull it all together. We assume that observed values will have a standard normal deviation, meaning some extreme values are possible even with random variation. In order to know if our observed value is really different from that of our null hypothesis, we calculate the z-score. The z-score is essentially the number of standard deviations between the observed statistic and the null value. Z-scores provide a standardized value which captures a certain percentage of the values of a population. The z-score is equal to the number of standard deviations away from the mean that corresponds to our desired confidence level. The p-value is the probability of our observed z-score being greater or less than the z-score under the null hypothesis. If our alternative hypothesis states the observed z-score will be less than the null z-score, then we look at the right-hand side of the distribution curve. If we think it will be greater than the null z-score, we look at the left-hand side. If we have a significance, or alpha, level of 0.05, we would have a confidence level of 0.95, or 95%. This is about 1.651 deviations from the mean, so that is the z-score we would use. In a two-sided test, if we have an alpha of 0.05, we would have a confidence level of 0.95 or 95%. Two standard deviations from the mean includes slightly more than 95% of the values, so we use a z-score of 1.96 to capture exactly 95%. There are a number of online reference tables and calculators, as well as statistical programs that will help you determine your observed z-scores and p-values. Once you calculate the p-value, compare it to alpha. If it is below alpha, then we reject the null hypothesis. You may have heard people say that a p-value is statistically significant. This means that, statistically speaking, we believe that the observed differences are due to something other than random variation. However, you should keep in mind that statistical significance is not the same as practical significance. Let's consider the following examples of statistical versus practical significance. You may have seen headlines several years ago that noted a connection between intelligence and fry preference, or that going to university increases your risk of brain cancer. The first one may be a fun fact, and certainly is not causal. Plenty of smart people don't like curly fries, although personally I think they're wrong, but the second one seems rather worrying. Should you drop out of university to save your brain? The finding that attending university is linked to a higher risk of brain cancer is based on a Swedish study. The researchers found a 19% relative increase in risk between participants with the lowest level of education, primary school, and the highest, university degree or higher, with a 95% confidence level. So far, this is all very concerning. But what the headlines missed is the size of the association. The sample was of 2 million men over 18 years. Roughly 1 out of every 600 participants developed brain cancer. As the baseline group, that would mean that out of 3,000 men with only a primary level of education, 5 would develop brain cancer. A 19% relative increase over 5 cases is 1 additional case. In other words, only 6 men with a university education are expected to develop brain cancer out of 3,000. The reason the study has statistical significance, but not much practical significance, is due to the very large sample size, so that even very small differences, such as 1 additional case of brain cancer, are magnified. Given enough data or enough tests, you can torture the data into saying anything. But much like torture in real life, just because the data tells you something doesn't mean it's true or valuable. For a detailed example of how multiple testing can lead to p-hacking, I suggest you read the XKCD cartoon on this slide. The URL is xkcd.com/882. The bottom line is, don't torture your data. It deserves better. So what did we learn in this lesson? Here are the key takeaway points from this lesson. 1. Hypotheses are predictions about the data. 2. Choose appropriate tests. Not every test will work for every type of data, and an inappropriate test will give you wrong or meaningless results. 3. Consider possible sources of errors and plan ahead to prevent or reduce them. 4. Finally, always remember that not rejecting the null hypothesis is not the same as saying the null hypothesis is true, and accepting the alternative hypothesis is not the same as saying the alternative hypothesis is true. We don't actually know, but we have made our best guess with the data and the tools that we have available. In the next lecture, I'll discuss detailed examples of one-sample hypotheses and two-sample hypotheses. Thank you.